bx squared plus 8x1.
Plus 1, you said?
Yep.
Okay.
And it says it has a horizontal.
All of a sudden, I'm not able to hear you very well.
Oh, sorry. It also says it has a horizontal tangent and a point of inflection for the same value of x. So it wants you to find the value of b, and it gives you a couple options.
A horizontal tangent and an inflection.
Mm-hmm.
Okay. Do you have the x value?
I don't have an x value. It's
Okay.
just at some point.
Okay. All right. Well, yeah, let's go through this. So horizontal tangents occur when the derivative is 0. And this is the correct function here?
Yep.
Okay,
I'm
so
mainly wondering, because it is a multiple choice, so I do have a couple answers, because I didn't see a real way of doing it without like brute force plugging things in.
yeah, I mean, one of the first things I noticed here is you got a cubic with your, that's why I ask if this is correct, because it's there's almost no possible way to solve this by setting it equal to 0, because your horizontal tangents occur when the or unless this is the derivative. Is this is the given the derivative or the original function?
It's the original function.
Okay. Yeah, I mean, you got problems here. I mean, you can't really set this equal to 0. I mean, if you had a calculator, you might be able to get away with something here. Now your second derivative, 12x squared plus 2b. Problem here is this is never equal to 0 unless b. Well, I guess b we could do it. Okay, so we set this equal to 0, but b then has to be negative. So x squared equals minus 2b over 12. So you can see the problem here is for this to work, x has to be plus or minus the square root of minus b over 6. So b has to be less than 0. You guys said you got some answers, some possible answers?
I do have possible answers. I'll just type them. It's -6, -1, 1, or 6.
Okay. I'm gonna graph this and see if I can come up with something. This is a very obscure problem. Where did this come from? I guess would be an important question I'd like to know.
It's like a review book I got.
All right. Yeah, I mean, and you said that the horizontal tangent and the inflection point are the same, but we don't know the value of b.
Mm-hmm.
Okay, so a b of -6 does appear to give the right thing we're looking for. Let me snip this in so you can see it. So that this comes around and connects, but this is a b of -6, but this happens at x equals 1. This horizontal tangent, and it's a change of inflection. But you're not given b. You're not given b. You're not given. You're just given the options. It says which of the following.
Yep.
Okay. Yeah, I mean, in that case, you are supposed to use the answers at the derivatives. That would be the only way. Like you'd have to plug in your x values in here to do that. You might you might be able to, is this a calculator section or non-calculator
This is
section?
not a non-calculator section.
Okay. Okay. Yeah, I feel like I feel like there's almost no reasonable way to determine this by hand. So I'm not sure I could be much help on this. This is also outside the scope of the type of question you would see on an AP, because they generally give you these constants that you solve for. When you take a derivative, you can actually get something from it. Like you can factor out an x from both and a 2 out of both. And like if the 8 wasn't there, this would be kind of a reasonable question. But I'm sorry, I'm not going to need much help on this.
It's okay. I mainly wanted to know if like there was some way to solve it without kind of having to plug in everything.
That would appear to be the only way. And which of the following questions are written that way, where you have to try the answers?
Fortunately, just one that I have.
So what else?
More conceptually wise, I wanted to go over limits.
Okay. Sounds good. Let me look for some problems here to kind of. All right. So let me grab a graph here. This is kind of the best place to start. So if I give you a graph of something like this, a few things are always true. One-sided limits always exist. And what I mean by one-sided is, for example, I can ask you the limit as x approaches, oops, it's in the wrong spot. I've done one of these a while. Limit as x approaches 0 from the left, that's a one-sided limit. Limit as x approaches 0 from the right, that's a one-sided limit. So this whole thing, consider this whole thing to be f of x. Do you recall how to figure out these one-sided limits? 0 from the left, 0 from the right.
Kind of, not really.
Okay, so from the left, this, and I actually think that wording is very important. From the left means you literally, here's 0, you approach it from the left, like you trace along the curve from the left. And how far down does this go? Well, it goes to minus infinity.
Okay.
Now 0 from the right, you're coming from the right. So what does it approach?
2.
2. Okay. So the thing is the other thing here is that it doesn't actually have to approach a value that exists. It's like a destination that you can't get to. Like maybe a mirage is kind of the example I used to give. You know, you think it's there, but it's not. It doesn't necessarily have to be like a fixed place in space. It can be something that you just see out there.
Okay.
So that's the kind of the first thing. For the limit to exist, for the two-sided limit to exist, we'll talk about that first. It has to approach the same value from the left and right. So for example, if I grab this graph again, snip it in here, and I ask you the limit as x approaches 2 of f of x, what I'm really asking, well, is the limit as x approaches 2 from the left, f of x, the same as the limit as x approaches 2 from the right, f of x? So from the left, from the right.
Okay.
And what would that be? Can you tell me that?
That would be 0.
Yes. So now, can you tell me a place where the limit does not exist?
The limit does not exist at 0.
Okay, I agree. Anywhere else that you can say that it does not exist?
I'm not sure about 3.
Okay, so let's look at 3. Limit as x approaches 3 from the left, f of x. Limit as x approaches 3 from the right, f of x. So here's 3, and here's from the left, here's from the right. So imagine this is you, and you say, friend, I want to meet you here, and your friend goes there. Are you at the same place?
No.
No. So numerically, one is this is a value of 1. This is a value of 2. These are not equal. So the limit does not exist. Now this graph here doesn't contain, so I'll make a graph here that does. There's that, and we'll call this, I don't know, A. What is the limit as x approaches A from the left? And I guess we need a number here. Call this 4. What is the limit as x approaches A from the right? F of x, because this is f of x, both f of x. So from the left, what's the y value? It approaches 4. From the right, what's the y value?
Also 4.
4. So does the limit exist?
Yes.
Yes. Okay, because they're equal. Now a different question, but I could ask you, let me just make this 3. Maybe that'll be, because maybe you'll go and look at this later and it'll be confusing. What is f of 3? Meaning, what is the output when x is 3?
There is no output.
Yeah, it does not exist. But the limit exists. That's kind of awkward, uncomfortable. It's like, what do you mean it doesn't exist? Well, there's nothing there. Like it's like, I kind of liken it to like you're approaching a river and there's no bridge. You know, you're both there, you can see each other, but there's no, you can't get across.
Mhm.
Okay. So that is one part of limits. You got one-sided limits, which always exist. Two-sided limits sometimes exist, and so on. So there's this kind of this like progression. So for something to be continuous, the following must be true. The limit as x approaches A from the left has to equal the limit as x approaches A from the right, has to equal the functional output at A.
Okay.
So I'll go back to this graph here. Actually, let me see if I can grab a different graph. Okay, so is this function continuous at x equals 0?
Yes.
It is, because the limit as x approaches 0 from the left is 0. The limit as x approaches 0 from the right is 0, and f of 0 is 0. How about at x equals -1?
No.
No. The limit from the left is infinity. Limit from the right is negative infinity. No way. Okay. So they all have to, 3 have to be true for it to be continuous. Okay. So now let me draw a graph here. That's filled in. And let's, let me just make some errors. This is 2 and this is 3. Is it continuous? at x equals 2.
Yes.
The limit, yeah, as x approaches 2 from the left is 3. The limit as x approaches 2 from the right is 3. F of 2 is 3. Okay, but, okay, we can now talk about the next thing, which is it differentiable? So now this is kind of a different question. So it's not really related to limits. It's like an extension of limits.
Mhm.
So the problem here is the slope from the left doesn't equal the slope from the right. So the answer is no.
Okay.
So there's some things here that there's like a progression. So if it's differentiable, that means it's continuous. But just because something is continuous,
Doesn't mean it's differentiable.
that's right. And that's where you get into this like standardized test stuff where you can get some weird questions where you got to really be careful here about what's happening. Okay, so that's kind of a starting point of limits. I don't think those are on the AP. I don't know. They're very common on just like university calculus exams. The other style of question you get with limits is this one. So the first thing you always try with limits like this, algebraic limits, is you just put the value in. And when you do that here, you get minus 25 over minus 5, which is 5. And you think, wow, this is really easy, right?
Mhm.
But it's not. So then you get to the next problem, and you get a problem here. You get, when you put 5 in this time, you get 0 over 0. You hopefully learn this at some point. This is indeterminate form.
Mhm.
Hopital's rule, or L'Hopital's rule, as it's correctly stated. Back when you first learned this, you were told like, well, use some algebra like factor, but when you get this indeterminate form, you can actually just take the derivative of the top and the bottom. Now, are you doing this for an AP or just like general knowledge, or for this class?
AP.
Okay. So if you're on multiple choice, they don't care how you do it. So you would want to use L'Hopital's rule because it's fast. 2x, take a derivative of the top, 2x minus 4. And then you go back to step 1. You just try it again. 10 over 6, great. 5/3. And most of these limit problems where you used to have problems with indeterminate form become way easier. So you don't have to mess around with them as much. So a problem like this, which kind of appears to be a pain, you can actually take the cube out. You can do the cube root out and just take the limit as x approaches minus infinity of x minus 3 over 5 minus x. And you again get this indeterminate form. You get infinity over infinity.
Mhm.
You take a derivative. Limit x approaches minus infinity, 1 over minus 1. So, and you have the cube root there. So the limit of this inside part is minus 1. So it becomes the cube root of minus 1, which is minus 1.
Okay.
Do you remember doing this?
Oh yeah.
Okay. So I think like the real power is in a problem like F, where there's this, let me get it snipped in. F is one of these like first calculus exam, horrible questions because there's this non-obvious thing to do. When you put 3 in, you get 0 over 0, you get indeterminate form, but you can take derivatives of the top and bottom. So it's 1/2. Well, I don't know. So one of the things that I think students don't get, at some point you got to look at the derivative square root of x is 1/2 square root of x, because almost every time it's written in this form, you're going to see something that's much more useful. If you keep going down this path of, well, it's x to the 1/2 and then it's 1/2 x to the minus 1/2, it's not going to be very helpful in the long term, because you really do need to use it in this form. So in this problem, it's 1/2 square root of x plus 1 is your derivative, the top, and then the bottom is 2x. Okay. Limit as x approaches 3. Okay. So now you can just put the number in. You can just say, oh, it's 1/2 square root of 4/2 times 3, which is 6. Square root of 4 is 2, so it's 1/4 over 6. It's 1/24, which is way easier than what you have to do before this, which is multiply by the conjugate. You remember doing that, which is the top and bottom. So, I mean, I've spent a little bit of time here on limits. Is there something else on this topic that you would like to discuss, or maybe a new topic we can look at together?
I think that covers most of limits. Another thing I kind of want to go over is a lot of the different rules for differentiation,
Okay.
because I think I know a lot of them, but I want to make sure.
All right. The big ones are that you've got to, well, the rules that I think could be in play here would be like product, quotient, and then chain rule. But chain rule actually applies to everything, so you can think you know it but don't. There's also obviously a lot of others, like power rule. There's that's really it. Then there's like functions. There's like, you got to know how to do, ln and e and sine and inverse and all these other things. So, I mean, here's kind of a classic AP problem. X plus 1 squared. Let me make 3x plus 1 squared. 2 minus 5x cubed, and they would ask for the derivative of this. Oh, and then implicit differentiation is also a good one. So when you look at this problem, like, what do you see? What kind of is your overarching guiding derivative rule for this?
Well, it does use product rule.
It's definitely product rule. So a lot of ways to do it. Keep the first, derivative of the second. Now the derivative of the second, it's power rule followed by chain rule. It's 2 minus 5x squared, derivative of the inside function minus 5. Plus, okay, derivative of the first, 3x plus 1, power of 1, derivative of the inside is 3, 2 minus 5x cubed. Okay, so now, like, you feel like in your class this would have been fine, but on the AP, what they will do is they will actually factor out things. So you've got a 3 and a 3 in both of these. So there'll be a 3 on the outside. You've got a 3x plus 1 here, you got 1 here, and then you got a 2 minus 5x squared there. So it's like, well, what do you have left over? Well, you've got one of these and a -5. So -5, 3x plus 1. And then here you got a 2 and a 2 minus 5x. Okay, and then from here, I mean, there's a lot of things they could do from here. They probably like distribute this as -15x minus 5 plus 4 minus 10x, and then they combine like terms. So -25x minus 1, and then they bring the rest of this down. And that's one of those things that you haven't seen in your class because your instructor probably was like, yeah, you don't have to simplify derivatives, but the derivative, because they're gonna put a bunch of these. They're gonna put one where there's a 2 here and a 1 here. You know, they all kind of look the same.
Mhm.
Maybe they take the negative out of this and put it in front. I don't know. They could do a lot of things. So that's an example of product rule. Quotient rule. I mean, and I'm sorry. So there's also logarithmic differentiation. But here's kind of your classic quotient rule problem. So it'd be something like 3 minus 2x over 4x plus 5 to the power of 3.
Okay.
So it's a power rule with the chain rule that's a quotient rule. So you gotta start with this one on the outside here. You gotta 3, keep the inside squared, and then you multiply by the derivative of the inside. So the derivative of the inside is the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. So from here, they probably would simplify the numerator. That's minus 8x minus 10. And then that would be minus 12 plus 8x. So you'd get minus 22 over 4x plus 5 squared. But notice over here, you got a 3 that would probably eventually combine with that minus 22. And then it's 3 minus 2x squared over 4x plus 5 squared, because then you can combine these bottom ones. Minus 66, 3 minus 2x squared over 4x plus 5 to the power of 4.
Okay.
And that's your derivative. Did your class cover logarithmic differentiation?
It did.
Did, okay. I have no idea if that's emphasized on the AP. But we've done a couple of, now we've done a product and a quotient with chain rule in both. You can get problems with just the chain rule, like y equals sine of cosine of e to the x. And this is just chain rule. So your derivative, you start with the outside function. Derivative of sine is cosine. Sorry, there's a small lag in there. There it is. Derivative of sine is cosine. Keep the inside function, which keeps the next inside function. Take the derivative of cosine. Derivative of cosine is minus sine. Keep the inside function. And then take the derivative of the last one, which is e to the x. Like that. Is there a particular derivative that you think we should look at, like a question from your book? Also, from what I remember, the AP never asks for just like something just like take the derivative, like maybe just like a product rule they would, but it's more like, where is the tangent line horizontal? You know, where does the derivative have a vertical tangent or something like that?
And that's tangents are basically you find it through the point at the derivative, right?
You set the derivative equal to 0.
Mm-hmm.
So like maybe a problem like this, they could say y equals x squared natural log of x, where is the horizontal tangent? So you have to be able to take a derivative of this, x squared 1 over x times 2x natural log of x, and you set it equal to 0, but let me simplify here. Plus 2x natural log of x. So you set this equal to 0, you factor out an x, 1 plus 2 natural log of x equals 0. So this occurs when x is 0, that's one of them. And then when 1 plus 2 natural log of x equals 0. And so that's where you get your prerequisite stuff coming in. You got to know how to do this. X is e to the minus 1/2 is your other one.
Okay.
So you got to know your product rule, your quotient rule. You got to be fast. You got to recognize chain rule within all of them. So then we just mentioned logarithmic differentiation. So let's say I give you natural log of, I don't know, x squared plus 3x divided by x to the 5th minus 4. They wouldn't tell you. You would just have to know how to do this one. And the best way is to rewrite it, is to say, oh, this is the natural log of x squared plus 3x minus the natural log of x to the 5th minus 4. And then the derivative is 1, well, it's over itself. And then you take the derivative, so 2x plus 3 minus itself on the bottom, 5x to the 4th. So this is one type of logarithmic differentiation. The one that you're probably more used to seeing is where it gives you something else that I'll show you here shortly. But any questions on this?
Yep.
Okay. And I don't even think this is an AP question, but this is the classic question. It's like, what's the derivative of x to the x? Okay. It's like, I mean, what does this even mean? I mean, it's a variable raised to itself, you know, like 9 to the 9. I mean, I don't know. It's conceptually very weird because it doesn't mean anything. But when you do logarithmic differentiation, what most people think of, but I wanted to show you both, is that if you take the natural log of the left and the natural log of the right, you can bring the exponent out. So you use logarithmic or ln differentiation when you have a function in the exponent. Okay, and usually the base is also a function. Okay, so now we'll get to the next part. So the power here is that this thing that's in the exponent, x, comes out in front. All of a sudden, you can take a derivative of both sides pretty easily. The left side is y prime over y. The right side is product rule. And so the form of these is almost all the same. After you do your simplifying here, you move the y over, the y comes over. So the answer always has times the original thing. And your original thing was x to the x. So your y prime is 1 plus natural log of x, x to the x. And so they could ask you, where does this equal, where does the horizontal tangent, where does this equal 0? Well, x to the x actually never equals 0 because you can't have 0 and 0 there. But you can set the inside part equal to 0. And you get x equals e to the minus 1 for that.
Okay.
So here, we don't have to do any of these, but like, here are some other possibilities. It would be like x to the sine x to the x, natural log x to the cosine x. then there's, an infinite number of these, but they're all the same. You do the same, ln of both sides, product rule. It's almost always product rule. Could be a quotient rule in some scenario I'm not thinking about. All right. Oh, implicit derivatives. This is important. Implicit derivatives. You're definitely going to get some of these on there. So for example, I could say x squared plus xy plus y squared equals 3. Do you remember how to find implicit derivatives with y?
Somewhat, is it something to do with you multiply the y by dy over dx or something? It's weird.
Okay, so so I'm first going to just rearrange this because it'll make more sense when we move through it. So when you take the derivative, you treat x as you always do. With y, you treat it like an x, but then you, like you just said, you multiply by dy dx. I prefer y prime. Do you really prefer dy dx? Because I can do that.
I can do either.
Okay, so y prime, but only when you're taking derivative of y. That's the case, and we're going to see that here. So the derivative of xy prime is first times the derivative of the second. The derivative of y is 1, but it goes with a y prime. Plus, derivative of the first is x. I'm sorry, derivative of the first is 1. You keep the y, so you don't need a y prime. And I suggest this to some students is they just remember this. Like if you don't want to think that hard about it, like this is probably the most common one you'll see.
Mhm.
that you could just go with, this right here. So that replaces all this stuff. Derivative of a constant is 0. Okay, so now the next step is to get everything but the y prime terms on the other side of the equation. So you're going to subtract 2x. You're going to subtract y. So you got 2y, y prime plus xy prime equals minus 2x minus y. And then you almost always factor out a y prime. And then you divide by this. So you get y prime equals minus 2x minus y over 2y plus x. And this is where the fun of multiple choice begins. There is no fun here. It's like there's a number of ways this could be presented. It could be minus 2x plus y in parentheses. The bottom could be x plus 2y because they prefer that order. They could put the negative out in front. There's a number of ways to do this. It gets really awkward when there's a minus and the plus in the bottom and the top because they could actually feed it in either place. So you may do all the work and not be able to find the right answer, which adds time, which you don't have on it. Is it like 60 questions in 60 minutes? Or is that too many?
Sounds about right. I can double check real quick.
Oh yeah, no need. But you got to be fast, I guess, is the point. You can't.
Mhm.
And I think one of the mistakes students think is like, oh, it's like the SAT. It's actually not. I think it's actually there's not like easy questions. I think they're all pretty time intensive.
Which is fun.
Yeah. There's actually a huge difference between the AP calculus and then first semester of calculus in college. It's very, very different, taught very differently also. Okay, we got 10 minutes left. Is there another concept, topic, some questions that you would like us to look at?
I guess concavity real quick.
Okay, concavity. So concavity is your second derivative. Your second derivative at a point is greater than 0, that means it's concave up. And there's a couple of types of concave up. There's this type of concave up, which is actually decreasing. And then there's this type of concave up, which is increasing. You can see that this one is increasing. This one is decreasing. And then the other possibility is that the second derivative is 0. And that means it's concave down. And some students do this like hold water, doesn't hold water with their hand. Your hand doesn't hold water because it'll slip through your fingers, but maybe you like the visual. I don't know. It's totally up to you. I think there's better analogies for this, especially if you've ever climbed a hill. But concave down means like this is decreasing, this is increasing. Okay.
Okay.
And then the problems that there's the next part, which is, well, where does it change concavity? So let me just graph something real quick. Okay, so let's say your function, your y is x e to the x. Your derivative is product rule. So that's x e to the x plus e to the x. And if you were to set that equal to 0, you could factor out an e to the x and get x plus 1, which means that x equals -1, something's going on. Okay, it's actually a min there, but that's not important. Your second derivative, you have a choice here because we're interested in concavity. You could actually go with this form or this form on the right. No. Do you have a preference?
I don't really have a preference.
So one of the nice things about the form on the left is that when you take the derivative of this, you've actually already done it. It's right up here. The derivative of this is this whole thing because you already did it. So the derivative of this is x e to the x plus e to the x. And then the derivative of e to the x is e to the x. And you can do this to save time. If you see that you've already used something, that's really great. So that's x e to the x plus 2 e to the x. You can set that equal to 0. E to the x factors out. X plus 2 equals 0. So your second derivative has a possible inflection point at -2. So when you check, do a sign chart here and you check points, e to the x is always positive. So it actually doesn't matter what's going on there. So for values over here, it's negative. For here, it's positive. So only when you go from minus to plus or plus to minus do you have an inflection point. This region on the right here, it's concave up. Here, it's concave down.
Okay.
And this is, from what I remember, this is kind of the style of the AP, is they would ask you, like, where is the inflection point? Or on what interval is it concave up or down? Something where you have to take a derivative and another derivative and do some algebraic manipulation. You will be expected to do that on the exam.
Mm-hmm.
What else?
I can't. Oh, I guess piecewise functions real quick.
All right, let me find one. Well, I'm finding one. I'll leave you with the comment that if this is, I think this is a good strategy, is to take like 3 problems and see if you can do them in 3 minutes, and then increase to like 5 problems in 5 minutes, and that will help you get comfortable with the format of the test being very intensive with time. All right, so blah, blah, blah. Okay. Here is your classic kind of piecewise question that you might see in this. So it says, we actually talked about this earlier. For something to be differentiable, it means it's also continuous. And that's important because you have to first evaluate the function at 1. And you have to set it equal. So you get 3 equals a plus b. And this is a problem because you've got one equation and 2 unknowns, no good. But differentiable means you got to take the derivative. So when you have a piecewise function, its derivative is also piecewise. So it's 6x power rule. Bottom, actually you're supposed to put the limits in or the interval in. Bottom is a, okay? And then this is where I think it's confusing, but you still plug that point in. And here it's just nothing. It's 6 times 1 equals a. So a is 6. Put that back in here. You find that b is minus 3.
Okay.
I've got one more like that here. Why don't you try this one? It's exactly, no. Sorry, this one doesn't have any values. Never mind. I'm just trying to find another problem. I don't know if we'll be able to. But let me grab this one real quick. We'll close out with this. So kind of same situation here. You got to try it at 1. So you have 1 plus 3b times 1 plus 2 times 1 squared equals m times 1 plus b. So you get 1 plus 2, that's 3 plus 3b equals m plus b. And if you just move this over, because I think this one's a little bit harder, you get m minus 2b. But again, same problem. You don't have derivatives. So you take your derivatives of each, 3b plus 4x, and then m down there, and then you try it at 1 again. So you get 3b plus 4 times 1 equals m, and you get 4 equals m minus 3b. So system of equations, you usually want to solve by adding and subtracting. We'll subtract. Minus 1 equals b, and then go back to one or the other. I'll use the first one there. M is 3 plus 2b. It's 3 plus 2 times minus 1. M ends up equaling 1. But you always try the point in the original and then in the derivative.
Mm-hmm.
All right, well, that does take us to the end of our lesson for today. Thank you for scheduling. When is your AP?
Tomorrow.
Tomorrow, okay. Well, probably more important to get a good night's sleep and, try to have as little anxiety as possible. That usually helps more than anything.
Thank you.
You're welcome. Thanks for letting me help you all semester, and I'll be available in the future if needed. Have a great night.
You too.
Night.